Aphantasia is the term for people whose imagination contains no visual features. Thinking of an apple brings to mind the concept of an apple instead of a picture. On the opposite end of the spectrum is hyperphantasia, or extremely vivid sensory imagery. The way that mental imagery ability is currently assessed is via one metric called the Vividness of Visual Imagery Questionnaire, or the VVIQ. A score of 16 means completely conceptual mental representations, and a score of 80 is imagery as vivid as actually seeing. This is the most popular metric we currently have for imagery classification. Most often, two groups are compared to one another, those with strong to weak aphantasia versus those with moderate to vivid imagery. Some studies suggest ambiguous imagery scores should be removed from analysis to try to artificially increase differences between groups. Also, only within the last 2 years, hyperphantasia has been distinguished as its own category in studies of visual imagery differences. As you can see, the classification of different imagery abilities doesn't currently have much agreement, and depending on how you categorize your sample, you can likely achieve vastly different results. My hypothesis is that relying on arbitrary VVIQ cutoffs and arbitrarily merging groups differently might create noise in meaningful data. So my collaborators and I came up with an interview method to categorize people into 4 meaningful categories that we could compare to one another. And the goal was to determine which groups showed differences from each other, and whether any particular pair of groups contribute most strongly to the imagery differences we find in the literature. Participants took part in a test battery summarized in these tables. The table on the left shows all the various comparisons we made to find out which groups are the most different from one another on subjective ratings. These include imagery vividness in different modalities, the ability to project imagery into the real world, visual working memory strategies, and features of pseudo-hallucinations in the Ganzflicker. The table on the right shows our group comparisons on objective measures, including visual working memory precision, congruency effects in priming, and visual long-term memory precision. I will highlight just a few of the tests in the run-through here. Ganzflicker is a rhythmic red and black flicker that elicits pseudo-hallucinations. Previously, we found that people with more vivid imagery see more complex things in the Ganzflicker. Here's a correlation matrix of Ganzflicker complexity ratings with VVIQ score. Pseudo-hallucination reports go from simple to complex along the y-axis. You can see that none of the people with complete aphantasia, shown in blue, saw complex objects, whereas about 2/3 of the hypers saw complex real-world objects and environments. In the long-term memory task, participants first saw a sequence of words and pictures of concrete objects. 24 hours later, they were tested on their memory for these items. Half the items changed format, that is, words turned into pictures and pictures turned into words, and participants had to indicate whether the item was the same or different format from the training. The biggest difference between groups here was whether people were able to remember correctly that the item stayed the same. The difference in accuracy is particularly driven by hypos, who show the poorest accuracy compared to all other groups. Aphants and hypers show precise memory for both words and pictures, whereas typical imagers show a benefit for picture memory only. In an adapted Stroop task, participants were shown color words, red, green, or blue, in random order. 32 milliseconds before the word appeared, the screen would flash either a congruent or incongruent color. A previous study by Cui and colleagues in 2008 found that the congruency effect on this task correlated positively with bold activity in V1, suggesting people with stronger sensory imagery representations were more accurate on congruent trials than incongruent trials. Our results were particularly driven by a difference between hypos and typical imagers, in that hypos showed the weakest congruency effect and typical imagers showed the strongest congruency effect. Participants also completed a classic visual working memory precision task, where they had to remember an orientation of a grating over 4 seconds. The grating changed either by 3, 6, or 10 degrees of rotation. Although there was a general effect of task difficulty, there were no group differences in accuracy on this task. Interestingly, we did find a difference in working memory strategies in the different groups. People rated the use of 5 different strategies: spatial, visual, sensory motor, semantic, and verbal, shown in green, blue, pink, purple, and orange confidence intervals, respectively. The biggest difference was in the use of visual strategies. Aphants and hypos were much less likely to use a visual strategy compared to imagers and hypers. So it seems that subjective differences between imagery and aphantasia are mainly driven by differences between hypers versus complete aphantasia, demonstrating the biggest subjective differences for the most extreme forms of imagery. More objective differences between imagery and aphantasia are mainly driven by differences between typical imagers versus hypos, perhaps suggesting that they have more similar visual representations compared to the extremes. But imagers may have stronger and more precise visual representations than hypos. If you like my poster and would like to learn more, please visit my website where I have a longer talk based on this project in my videos. You can visit my Google Scholar page or follow me on Twitter to get the most current updates on my work. You can click on the links in the PDF of the poster, as well as try out all experiments discussed today by clicking on the little running person next to each experiment. Thank you very much.